Hello and welcome back to Multidimensional Integration, the video series where we talk a lot about the different possibilities to integrate a function in higher dimensions. And indeed, in today's part 12, I want to connect such an abstract integration with the standard partial derivatives in Rn. And after that, we will see when it is allowed to differentiate under the integral sign. Or to be more concrete, we want to push a partial derivative into the integral. However, before we go into the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a member on Steady or Patreon, you can download a lot of additional material for the videos. I think this is really helpful because you can also just download the PDF version for every video. And then without further ado, let's immediately go to our space Rn where we have partial derivatives. For example, you could just say we have an ordinary function F where the partial derivative exists. So the function f maps into the real number line and the partial derivative as well. And let's simply say that we fix the index j for the direction of our partial derivative. And that's good enough, we are only interested in that particular one. And now if we want, we could also say that the domain of definition is just an open set X in Rn. Also there, partial differentiability makes sense. However, now in addition to this n-dimensional space, we will put a different space to it. And this is the space where we actually want to integrate, which means it could be an abstract one. And in fact, abstract here means that it could be a whole measure space with a given measure mu. Everything works here in this abstract setting, but if you don't like it, then you can also think of our standard Lebesgue measure. In that case, you just would have our standard n-dimensional space here and a k-dimensional space with the Lebesgue measure there. But in any case, we would always just consider a measurable subset in our measure space. So let's call it y, and this one is quite important because we will integrate over it. But first, please note that we can easily consider the Cartesian product x with y. And this will be the domain of another function f. And maybe let's simply call this one lowercase f. And indeed, the two functions should be related, namely we would start with our lowercase f, and then by integrating over the set y, we would define our capital F. To make this more precise, let's say we consider f of two variables, x and y, and now for a fixed x, we just integrate over all possible y's. Hence, the resulting integral here is the value capital F of x. So this is the whole relation, we just need an integral over lowercase f. And this is over the set y and with respect to our measure mu. And that's it, the variable y will vanish because we integrate over it. Okay, so this is the relation between the two functions, and now we can ask what happens with the partial derivatives. Indeed, the question would be, can we just push the partial derivative of capital F into the integral such that we consider the partial derivative of lowercase f? Or in short, you could say, if we start with a differentiable function, is the new function capital F also differentiable? And the answer for this question is the important theorem of today. In short, we will learn about the differentiation under the integral sign. And now for the start, let's clear up all the assumptions. So we have our space Rn and the measure space as before. And they are defined on the Cartesian product. We have an ordinary real-valued function. And it should have the property that for every fixed x, we can integrate over y. This means if we look at a function that is only defined on the set y, then this should be an integrable function. So it's integrable with respect to our measure mu, and it does not matter which x in our set x we fix. So this implies that our function capital F is well defined on x. So these are the natural assumptions we definitely need to make sense of the whole picture. However, to get the differentiation under the integral sign, we have to assume two more things. First of all, because we want to talk about partial derivatives, we need to assume that the partial derivative of our lowercase f exists. And in fact, the best thing would be that it exists no matter which pair of points xy we choose. Or to state it differently, for every fixed point y, we want to get a function defined on x. So our special partial derivative gives us a well-defined function on x. And there we can see the point y just as a parameter for these functions. Indeed, in the end, we also want to be able to integrate over y. And for that reason, we don't need this assumption exactly for all points y, because we already know that the integral allows for some exception points. And in measure theory, we just call this property mu almost everywhere, which means we can have an exception set of measure 0. This makes sense because the integral will simply not see this exception set. So this makes the whole assumption a little bit weaker, because now it says we can calculate the partial derivative for almost all y, but definitely for all x. And now comes the second assumption. We want that this new function is a continuous function from Rn into R. In other words, we want that our lowercase f is partially continuously differentiable. And this is a property that should translate to our function capital F as well. However, in order to get that, we have to require the existence of a special integrable function. And maybe let's simply call this function g. We can say it's a non-negative function defined on y, where the whole integral is a finite number. And moreover, it should be something we call a majorand for our partial derivative. This means if we take our function given by the partial derivative and go to the absolute value, then the value of this function is always smaller or equal than g. So it's an integrable majorand for the partial derivative because it always lies above the function and it's still integrable. So it does not matter which point x and y we put in here, we always have this inequality. The only thing we can make weaker as before is that for y we can ignore an exception set of measure 0. And with that we have all the assumptions and we can finally state the conclusion. And maybe not so surprising, what we get is that the partial derivative of capital F also exists. And moreover, we can also see it as a map from x to r, and then it's also a continuous function. And as you might expect, we also get the formula that we can push the partial derivative into the integral. In other words, the value of the partial derivative of capital F is given by an integration. So the formula is quite natural, but please don't forget what we need are the assumptions from above. Only then we can guarantee that the integral here on the right hand side has a finite value. But there we have it, this is the whole theorem, which is definitely really useful in applications. Therefore for us here, it's important that we can formulate a correct proof for that. And as you might already guess, we need some results from measure theory to get the general statement. Indeed, the integrable majorand might already tell you that Lebesgue's dominated convergence theorem is applicable here. In short, it just tells you if you have a sequence of measurable functions that are dominated by an integrable majorand g, then this allows you to exchange the limit and the integral sign. In other words, you can just push the limit into the integral. And in fact, such an exchange of limit processes is exactly what we want to do here as well. We just have to rewrite the differentiation as a limit process. And you should see here Lebesgue's dominated convergence theorem is so nice because it just needs the existence of this integrable majorand. And if you want to know more about the theorem and see a proof of it, please check out my measure theory series. Here we just want to apply it, so let's rewrite our partial derivative as a limit process. Which simply means that we can just go back to the original definition of a derivative. And to make everything simpler, let's simply fix a point x tilde, which is arbitrary, but we want to calculate the derivative at this point. And now you know, since we have an open set x, we can always find a whole epsilon ball around this point. So more precisely, we find an epsilon greater than 0, such that the whole epsilon ball centered at x tilde lies completely in x. And the common notation we have for this epsilon ball is b epsilon at x tilde. And now if you want to calculate a derivative at x tilde, we can just approach the point with points in the epsilon ball. And since we are only interested in a special partial derivative, we approach the point in just one line. Therefore, we can just choose a sequence of scalars in R that describe this line. So we can be positive or negative, but we should be inside the epsilon ball, but not at the point x tilde itself. But then in the limit k to infinity, we want to land at x tilde. So the sequence of scalars hk should tend to 0. Therefore, again, the points we consider will be given by x tilde plus a small deviation from it. And this one will be given by hk times the canonical unit vector ej. And that's all. Now you see, this is how we can describe a partial derivative of lowercase f as a limit process. So more concretely, the partial derivative of f with respect to xj is given by a limit k to infinity. And I don't tell you something new when I say that this is the limit of a difference quotient. But of course, to make it precise, we should write it down. On the left, we have the point as mentioned with hk, and y is not changed at all. And then on the right in the difference, we just have the value of f at x tilde. And here please note, the partial derivative has this form no matter which sequence hk we choose. And this fact we can use to calculate the derivative of capital F as well. Of course, there we don't know yet that the partial derivative exists, so we need to show it. And indeed, we can just show it by also considering this general limit. So in the same way, we deviate from x tilde and subtract the value at x tilde. If this limit exists and it has the same value for every sequence hk, we know that the partial derivative exists as well. And then it's exactly given by this limit. Therefore, in the first step here, let's put in the definition of capital F. So as a short reminder, it's just the integral over lowercase f, which means in the numerator here, we have the difference of two integrals. And then obviously we can put them together and also pull in hk. Hence, what we have in this integral in the end is just our difference quotient with lowercase f. So it's almost the partial derivative of lowercase f, but as you can see, the limit is still outside the integral. And now we just have to justify that we can actually pull it in. And this can be done by the standard mean value theorem of differentiation, because you could say that we just have a one-dimensional derivative here. In fact, the partial derivative can be seen as a straightforward extension of the standard one-dimensional derivative. So the mean value theorem is applicable here, and we just have an intermediate point that we can call psi k. And y does not change anyway. Therefore, the result we get here is that such a difference quotient can be always expressed by a partial derivative. And indeed, by assumption, our partial derivative here has an integrable majorand. This was assumption B, and it means that Lebesgue's dominated convergence theorem is applicable. And this finally allows us to pull the limit in. And this is almost the last step, because we already know that this limit is exactly our partial derivative at the point x tilde. So we get that the limit of this difference quotient here is always the same value no matter what hk is. Namely, it's always this integral of the partial derivative of lowercase f. So we can just conclude that the partial derivative of capital F always exists. It does not matter which point x tilde we choose, we always get out this formula for the partial derivative of capital F. And this is quite nice because it already gives us the partial differentiability of our new function. And now the last question we have to answer is if this partial derivative function is also a continuous function on the set x. And this is actually quite easy to show because you could just look at a sequence of points xk. We'll just say that xk converges in Rn to the point x. And now continuity would mean that this convergence translates to the convergence of the values as well. However, by the formula above, we just know that we find the sequence xk inside the integral again. This means if we want to calculate the limit of the values here on the left, we just have to push a limit inside the integral again. So you see, this is simply Lebesgue's dominated convergence theorem again. And that's already it. because now we can use that we know that the partial derivative of lowercase f is a continuous function. So you can say the continuity there is inherited by our capital F as well. And that's it. Now we have proven this nice and important theorem. And now I can already tell you that I have already discussed some examples where the theorem is applied. These are some other videos that I just link in the description. And with that, thanks for listening, and I hope that I see you in the next video. Have a nice day and bye bye.